So,
everyone, and thank you for joining our meeting reading group. Today, we are excited to have another great speaker, Daniel Povey. He is very famous for many of the toolkits and data sets that we know about, like Caldi and Libre Speech. As always, if you have any questions, feel free to raise your hand, ask your question to the speaker, or write your question in the chat. Without any further ado, the stage is all yours.
cool, thank you. So, I think this is going to take like way less than an hour. Like, honestly, it might be a 20-minute talk. So, I'm kind of interested to hear like what you guys are interested in these days and what kinds of projects you're working on and what things you're following. I know that isn't the normal part of the normal format of your reading group, but I think we could make an exception just this time and maybe I don't know, either go through people or maybe someone like Nicole could give me a just general intro to what people are doing. What do we think?
Sure. We can
Cool.
start with a talk and then discuss. Thank you, then.
Okay, fine. Okay, so to put this thing context, this CR-CTC. So we used to be mostly focused on ASR. And this, I guess this is the last kind of successful thing that we had while we were still primarily focused on ASR. Right now, we're doing most of our new work on TTS. We haven't really published anything. We don't have like a finalized recipe really for TTS, but that's the kind of thing that we're spending time with right now. We're mostly focusing on things like flow matching and I'm worried about the speed of the deployed models. So it turns out that the vocoder is actually a significant part of the time taken. So we were doing a lot of work trying to get a faster vocoder. It seems that the current vocoders like Vocos and I forget what the other one is, they're GAN-based things. It seems to be really hard to get much faster than those because they're already highly optimized. I was kind of interested in trying to get rid of the GAN aspect because GANs are super unstable to train. But it seems really difficult. We were trying things with flow, trying to get like fast flow-based vocoder. Again, that seems to be really hard to do in a reasonable size and speed and everything. So anyway, so that's the context of this. This work, we actually just presented this a few days ago. The guys, two of my guys, presented it a few days ago at ICLR, but this actual work is maybe at least 6 months old. So I guess you're a speech group, right? So everyone knows what CTC and RNNT is, and also CTC/attention encoder decoder. So CTC is always the preference for like efficiency, and the decoding is super simple and fast, but it's usually a bit behind the others in performance. And this work closes most of the gap. It makes it so that it might be more practical to use CTC on its own because there's really very little remaining difference. And it also gives additional improvement when you use it as an auxiliary loss. So the basic method is it's kind of a multi-view thing, where basically you add an extra loss. And what the loss consists of is we use the CTC like posteriors from the other branch, meaning the other view of the data, as the reference. We separate the gradient from that. We don't propagate through that, but we take the other half as the reference and we add it typically with a scale, I think, of about of less than the CTC loss. I have to check what loss scales we normally use. I remember the CR-CTC loss tends to be about 0.2, and I think the CTC loss maybe is 0.5. I know the CR-CTC loss is less than the CTC loss. I forget the precise numbers, but anyway, so it's this multi-view thing. Now the different views, it comes from different copies of spec.org. So as you probably know, in spec.org, you like zero out certain sectors, kind of rectangular sectors of the spectrogram. You like set them to the average. And in this multi-view CTC, sorry, multi-view SPECOG, we just do that with different masking regions. Now SPECOG, you might remember, also has an aspect of time warping. And to get this to work, we have to make sure to share the random time warping. Also, just for background, our implementation of SPECOG is just a little bit different than the original implementation that those guys released, because the original implementation, it was hard coded to have two masking regions on the time axis. Or you could specify the number of masking regions, but it was specified as a constant, like 2 or 3 or something. And that isn't really suitable if your utterances might be very variable in length. So in our implementation, it's configured relative to length. But anyway, another aspect of this is that we do increase the SPECOG time masked fraction. There'll be slides about this later. But basically, I think the masked fraction is usually something like 0.1 or 0.15. And we increase that to about 0.3 for this thing. So now, yeah, there's two things going on here. One is the duplication and one is the extra loss. And both of these actually give improvements. Okay. Okay, so this slide is about various explanations for why this works. As you'll see later, it does give really quite large improvements. Something like word error rate of, let's say, 6.3 to 5.5 or something like that, or maybe even more than that. Maybe it's even 6 to 4 point something. It's a big improvement. And this is comparing like the best numbers from each of the two rounds. So it's not necessarily epoch to epoch. That comparison is a bit tricky because we see twice the data per epoch. But in the end, it's even better. It's better also on a per epoch basis than CTC. Anyway, so some of the theories why it might work is, so our models, like most ASR transformers, are trained with some kind of layer dropout. Now, those actually have a time schedule on them, and they get really quite small towards the end. I don't believe this is the major factor, this layer dropout. The more recent versions of our zip former that I'm working on, we actually take out all of this randomization stuff. And so this aspect, I think, is not important. There's a self-distillation aspect. Yeah, maybe this is arguable. I don't know what that really means, though. It feels like there's not much difference between self-distillation and regularization. Using different augmented views. Well, obviously this is going to reduce the gradient variance, right? Because we're kind of in a sense, we're averaging over 2 copies of the data. Normally you don't expect it to be very efficient to reuse data when you could just be using twice the amount of data, right? And using each one once. So I don't know that this really fully explains it. Okay, so here is some experiments. This this looks like it's a Libre speech, like a 1,000-hour Libre speech experiment. So the CTC baseline is 2.5 and 6.0. The final CR-CTC is 2.1 and 4.6. You see, that's a huge improvement, right? You normally would expect from some slight algorithmic change that you could go from 6 to like 5.8 and, you know, to declare that a victory. We really weren't at all expecting such a big improvement from this. So this is an ablation experiment. The final number is 4.6. If we don't do the larger time masking, I think this means if we use 0.15 instead of 0.3 as the masked fraction, we lose, looks like we lose about 30% of the improvement on test other. Goes from 4.6 to 4.98. If we also don't have different masked regions on the two copies, meaning if we constrain it to use the same time masking, that gives us a further degradation of about 0.1. That's actually surprisingly little, because you kind of would have thought that that having different time masks is really the essence of the method. So it's a little bit surprising that when we don't do that, it doesn't hurt it more. If we use hard labels for the reference that comes from the other side's posteriors instead of the soft labels, it gives us a small degradation from, let's say, 4.6 to 4.84. That's not a huge difference, right? If we remove the stop gradient, it looks like it's hurting us by about 0.3 on test other, 0.1 on test clean. That's, again, it's not a huge difference. Theoretically, I would expect it would be necessary. I don't want to use the word theoretically. Intuitively, it makes sense to remove the stop gradient because, sorry, intuitively, I think it makes sense to have the stop gradient because otherwise it could encourage us to like have a flat distribution. Because that, I mean, if the distribution was just constant, that would kind of minimize the CR-CTC loss. That loss would be 0. But of course, that wouldn't give you a good CTC loss, though. So anyway, this is more about the reasons why it might work. So similar to mask-based self-supervised models. So I believe Jan LeCun was trying to push quite strongly. He has a thing a bit like this that he uses for like vision stuff, where they have 2 masked copies and you try to predict the other ones out. But I think he was advocating this at some point as some kind of very general solution to AI. So it has a little bit of the flavor of that. The fact that setting the time masked regions the same, to me, it makes me wonder whether this explanation could be true. Like, it makes me think this might not be all that's going on. Anyway, this slide has some other experimental comparisons. Let's go through this. So the CTC baseline is 2.5 and 6. If on the CTC baseline we have larger time masking, like 0.15 to 0.3, I think that gives a degradation. On our CR-CTC, that same change gives an improvement of about the same magnitude, about 0.3 on That's from the no larger time masking line to the CR-CTC final line. It's about 0.3. So it does help. No larger time masking, no different augmented views. Yeah, that means the same. Oh, I guess that means both of the masks are the same. That makes surprisingly little difference, doesn't it? 2.19 to 2.27. So it makes me feel like something weird is going on. And I will get to something a bit later. We try something very simple that gives also quite large improvements on CR-CT on CTC. I'll get to it a bit later. The last two lines here are about excluding in the loss the frames that we masked. Now, the last line is the one that kind of makes sense intuitively. We exclude self-unmasked frames in the loss. So this is effectively doing something like BERT or something. I think in BERT, you only count the frames that were masked on the other side or something like that. I know there are other methods of this flavor where they do only count them the frames that we masked in the loss. Anyway, it makes it worse. Okay, let me go into the next slide. So there is another aspect of this whole thing that is an alternative explanation, that it's about peak suppression in CTC. Because this CR-CTC, it does give us less strong, less peaky peaks. So these are just some samples of speech. And on the right is CR-CTC. On the left is regular CTC. And you can see that the peaks get a little bit wider and they're a little bit more fuzzy, I guess. So we tried a simple method of emulating this, that we just have one copy of the data, but we add an extra loss that's a bit like CR-CTC, but it's taking this output and then smoothing them out in time by convolving with the kernel, and then use that as a kind of reference. So we try a smooth kernel that's 0.25, 0.5, 0.25, and then we add like this extra loss to try to smooth out the peaks. And it gives us a surprisingly large improvement. So the CTC baseline is 6.02, and that takes us down to, sorry, SR-CTC takes us down to 5.22 on test other. So look, that's 0.8. Now, for something like this, you really wouldn't expect such a large improvement. You normally only get such a big improvement if your system was broken originally and you fixed something, right? So this, like this by itself, I think this would have been an interesting paper to the extent that people are still using CTC anyway. It's like a super easy way of improving the results quite a bit. And it's just a few lines of code. So, you know, if you don't want to do CR-CTC for some reason, and you do still use CR-CTC for something, you might want to consider this. I don't know that we even actually published any code about this, because it's not part of our standard recipe, but it's super easy to implement. Anyway, so here's some additional experiments with auxiliary heads. So normally we don't use CTC by itself. Normally we combine with either acoustic encoder decoder. Sorry, is it acoustic attention encoder decoder, or with RNNT? And basically it still gives an improvement. Let me okay, so this experiment, the CR-CTC itself is not combined with the other heads. It's just pure CR-CTC, but it's still better than those others with standard CTC. Now, in practice, we're going to combine the two. I guess this next experiment might have that. Wait. Okay, so yeah, we do have it. So this includes a bunch of previously published results. Apologies if your things are not referenced here. I don't know if they are. Let me see. So basically this compiles a bunch of published numbers, but in the end, like our numbers where we combine RNNT with CR-CTC end up being the best ones. I think we believe this is the best published numbers if you count things that are only trained on libre speech and that don't use an external language model. So let me look at this. So if we compare the three that near the bottom, the three that have CTC, and then go down to the ones that have CR-CTC, it's a quite big improvement, like 5.72 to 4.35. That's really quite big. And then if we go down to combining it with other things, that 4.35 goes to 4.08 and 3.95. So another, nice improvement. These are really very good numbers on libre speech. I think that the bottom two numbers, these will be decoding with the decoding with RNNT or with attention encoder decoder. So the CR-CTC is really just, I think, an auxiliary loss here, an auxiliary way to train those things. But it's still nice. AI shell. Okay. This is also some results on the AI shell data set, the Chinese data set. It shows you the same general picture. Quite big improvements, I believe. Let's see. CTC is like 5.26. CR-CTC is 4.12. This is with small. So yeah, big improvement. With GigaSpeech, the improvement is less, I think. It's still like non-trivial, but it's not as much as it was before. Let's see. So CTC zip form is small, that's 11.95. CR-CTC zip form is small is 11.58. So 0.5% absolute. This is obviously nowhere near what we were getting on GigaSpeech. I think we have to assume this is because GigaSpeech has so much more data that overfitting is less of a big deal, and maybe this had something to do with overfitting or reducing overfitting. It could also be that GigaSpeech just has a much higher noise kind of word error rate floor, but some of it's maybe some of the transcripts are wrong or something. It's hard to say, but I would guess that it's just less improvement on more data. Okay, let's see. Yeah, so here's links to the paper and the code. So yeah, that's it. In our general experience with this, I think what's going on is it's a combination of something specific to CTC, that maybe it was fixing some kind of problem with CTC, and also something more general about multi-view. So we always see more improvement on the CTC head than we do with the other heads. Also, we have tried to come up with a version of this loss function that's specific to like RNNT or attention encoder decoder. It's harder with attention encoder decoder because there isn't really time alignments, but we couldn't get anything to work on that. We couldn't get the version of this to work with RNNT. It was maybe too hard to find an appropriate loss function. I've also been trying. I'm working on a refactored and improved version of the zip former, and I have got a little bit further improvement by introducing a loss about predicting the original log mel before the augmentation. It's not a big improvement, but it's something. Yeah, maybe that's everything. I was hoping to hear a bit from you guys about what you guys are interested in these days, what you're working on,
Sure.
things like.
Sure. Thanks a lot for the talk.
Okay.
Maybe first we could start with a couple of questions in the chat. And if any of the audience has any questions, feel free to raise your hand and ask the question directly from the speaker. So one question in the chat is, do you have any intuition about whether different types of augmentation, like adding noise or reverberation, would work similarly under this setup?
Mm, You think, I don't see why not. I mean, it seems like a natural thing to try. I don't even know why we haven't tried it. I think it's maybe that because of the way our data loaders work, it's just not super easy to try that, but it definitely seems like a natural thing to try, yeah.
Okay. Another question is that in the no larger mask, no different view scenarios, are there still differences between the two model execution? For example, different dropout mask within layers.
Yeah. They are. They are different. And I assume that must be why it still helps, although it's surprising it still helps so much. In more recent versions of the format, I'm trying to take away all of those randomized things. Mostly because I'm thinking about using this for tasks like flow matching, where it's kind of a regression task, and I was concerned that introducing random things is just going to cripple the model too much.
I see. So I think Mirko has a question. Yeah.
Sure. Thank you for the talk. It looks like in your technique you're applying this distillation loss, right? The regularization between two augmented version, two
Yeah.
different augmented version. Did you try to consider like distillation between the clean, right, and the noisy one, right? So not
Oh,
noisy versus noise, but clean versus noise.
oh, I see what you mean. Let me think about this. I don't know if we ever really did that experiment. I think part of the motivation for having it be noise versus noise is that we if you were to do the clean one, you'd probably be mostly interested in that as a kind of reference, right? And then you wouldn't be wanting to backprop through that. Or if you did backprop
Yeah,
through it,
yeah,
you
you can
kind of be
detach in that
wasting
case,
it.
right? You can
Yeah, you can
detach.
catch it. Yeah, but then the thing is, that's going to slow down the training because what we currently do instead of doing forward twice,
Mm-hmm.
we concatenate them so that we just do once on the whole batch, right?
Mm-hmm. Mm-hmm.
So now, yeah, I don't know that we've tried that. My feeling is that it would probably just give a little bit less improvement if we were to do that. Yeah, might be worth trying.
Okay, then yeah, it looks like um if you increase the scale, like the return is lower, right? It's that just because
Yeah.
larger networks trains on larger data set are not are
Mm.
do not need regularization, or what's your like
Mm.
interpretation?
Yeah, I mean, I'm assuming this all has to do something with generalization and regularization and things like that, and that when the training data is so large, regularization is almost not an issue, and that it's all about
Mm-hmm.
can you fit can you fit the function. So I guess it matches less, although it still seems to help.
Yeah. Yeah,
Mm.
that makes sense actually. Yeah. And did you also try to, have like instead of two augmentations, having more, right? Like a three,
Mm.
four, five, six,
We
whatever.
haven't tried that. I mean, it might be interesting. Although my feeling is you'd get very rapidly decreasing returns.
Yeah. Yeah, actually, you ask ourselves what we are working on. Actually, there are many things, and one I have like one collaborator who unfortunately is not here, but Gianfranco, who is working on data augmentation, like on trying to see
Mm.
if we can do something better than spec augment, right? It turned
Oh,
out that you can do it much better than spec
really?
augment with if you, well, spec augment is very nice, it's very clean, right? But there are
Mm.
a few other artifacts and noise
Mhm.
types that you can add which actually makes sense. We are
Mhm.
studying that, like hopefully we
Mm.
will
Oh,
publish in a few months. But it
cool.
turned out that we also try something similar to what you like consider, like trying to distill, right? Uh, the from different like views, right? From different augmented data. And
Mm-hmm.
we also found beneficial, right, having different augmentations, not just two, but
Mm.
I think these days we are using with our latest things, we are using one. We are using in the same batch. We have the clean signal,
Mm.
right, and three augmented versions of them.
Wow.
But as you said, yeah, there is of course a diminishing return, right? Because you need to.
And what kind of losses are you using with that?
Well, we are using like KL divergence, right? We are running experiments with that. We
Mm.
will probably consider like also contrastive learning at some point.
This in the
Uh,
context of CTC.
it's actually done as in the context of encoder decoder and also CTC, right? Yes, yeah, we are trying to
Oh,
come out with something general, and we are also trying to
mm.
distill internal features, this kind of thing. But yeah, I think the main contribution for now is like the let's say the revised version of spec augment, right, where we actually add other contamination strategies, and that seems to help a little bit. But yeah, it's very related, and
So that works for you in the context of attention encoder decoder.
Yeah, yeah. We are trying different. We are focusing on speech recognition these days. We are like
Mm.
we have like a model on transducer, one model on CTC, and one model on encoder decoder. And yeah, seems to work, right?
That's
So
interesting. Maybe we
yeah.
should have done something with it. I think I thought after thinking about it, I convinced myself that it somehow wouldn't make sense for attention encoder decoder, but I guess it does. Uh,
Um,
there
you
is a
can, right?
distinction over the next word, so and I guess it could make sense to.
Yeah, as long as you can have probabilities in output, you can do distillation and give it a
Yeah,
try.
yeah, yeah.
Yeah. So let's see what happens on that side.
Hmm.
And I'm wondering if the
We
others
try
in the
that.
audience have other questions regarding this specific
Hmm.
project. I guess this was ICA's paper, right? Then?
This was ICLI.
Oh, I CLR paper.
Yeah, yeah.
Okay, good. And
Personally, I prefer going to ICAST because I know people there, but my guys want to go for ICLI.
yeah, there were many problems actually. Um,
Yeah, you mentioned it to me that it wasn't well organized.
yeah. If there are no more questions, maybe we can open up a little bit the discussion also beyond this specific
Cool.
work. Yeah, wondering, uh, you know, you are still working, right, on K2 and wondering what are your
Yeah,
plans?
yeah. Well, yeah, but mostly our most active work on it is really focused on TTS right now. Uh, adding TTS recipes and trying to come up with a really fast TTS recipe.
So you're focusing on efficiency, right? So
Yeah, mostly. Obviously, but also, to have like state-of-the-art results, but to make it faster than other things because like there's so much data that if you don't care about speed, you can really make it perfect. Like you can't really even tell that it's not real, right? So
yeah,
I,
yeah.
I feel like speed is really the only remaining thing that you can optimize almost.
Yeah, I think Nemo, right? They have something like that, as far as I remember. Yeah, yeah. So you
Right.
want to go low level, I guess, right? Low level, like uh, as low level as possible to maximize efficiency, or you have ideas,
Well,
right?
no, it's not that I necessarily want to like focus on optimizations for hardware or things like that. It's really it's just to have something you can implement that you can do inference on device and easily in real time and make it actually faster than
Mhm.
real time. I think you can easily target 10 times real time for something like a PC.
Mhm. That's
It,
interesting.
it
So,
turns out the limitation is actually the vocoder rather than the main TTS model.
uh-huh.
Surprising, but like even with things like flow matching, if you have a reasonable number of steps, like four, I think this thing ends up still being dominated by the vocoder.
I see. I really want your opinion on, everybody these days, including
Mhm.
our team,
Mhm.
Pune or Luca,
Mhm.
they are working on these audio tokens, right? So as a way to replace, like,
Mm.
instead of working with continuous
Yeah.
representation, we work with discrete representation that can be
Mm.
better, like feed into a multimodal LM. So wondering what's your
Mm.
takeaway about continuous versus discrete representations of like audio and speech?
Mm. Well, I, I, I mean, I'm not personally ever that eager to work with the discrete representations, partly because uh, I'm concerned that one of the motivations for doing that is because it makes it like a LLM task, and everyone wants to do LLMs because LLMs are so trendy, and I just don't like to jump on the bandwagon. Although sometimes in the past there have been times when I should have jumped on a bandwagon and failed to do so, but I just instinctively don't like to jump on bandwagons. And I get that you can get really good quality TTS, but these days flow matching TTS is also really, really good. Uh,
Yeah,
it's
for TTS, yeah.
Yeah. I mean, further, look, I'm sure there are situations where it might make sense to discretize, but uh,
But do you think it's possible to
mhm,
create a kind of um, discretization method which is universal in the sense that it works for everything, every task, it captures
mhm,
pretty much every relevant information inside speech? How do you feel about that? We are still not there,
mhm.
right? So our team is
Well,
benchmarking a lot of things. I'm wondering if, based on your expertise in the field, you think there is hope to go in this direction or not?
okay, okay, to me, it comes down to a question of what purpose are you discretizing? I feel like there are times when people discretize just because it's the trendy thing to do, but there were times when you don't need to discretize. Like let's suppose you want to as an input to an LLM. Some people sometimes discretize and then they train an adapter
Yeah.
or something, but you didn't need to discretize. You could have just trained an adapter directly from those embeddings, right? Uh, and I tend to view discretization as being uh, like think about the channel coding theorem from information theory. There's some kind of theorem that talks about the amount of information you need to uh, to encode a signal with less than a certain amount of noise. I think it somehow relates the number of bits you need to specify to the like variance of the noise or something. Uh, and the idea being that if you have a large enough code book and do it at a fast enough rate, you should be able to get the noise down. So I just view this discretized stuff as like a lossy or noisy representation of the signal. Uh,
Mhm.
and I feel like a lot of the times you could just use the signal without that. Or I guess there were sometimes when people do it. What's that thing where you integrate over the noise? It's like a noise bottleneck, but there's integration involved.
Okay, yeah, that's interesting point of view. I can kind of agree on that. And yeah, from what we have seen, right, so
Hmm.
far, pretty much with any tokenizer, like tested on different tasks like generative, discriminative tasks, ASR, announcements, all these kind of things. The continuous representation is better. There is still a gap. So maybe you're right when you say that, okay, there is inevitably we will lose some kind of information. Yeah. And then concluding this discussion about LLMs or multimodal LLMs, it looks like, and there is a clear trend, right? That essentially speech processing will be integrated within a multimodal LLMs, right? That is able to do ASR, speech announcement, and whatever. So, what do you think? What do you think about that? What do you think we need to? What do you think are the open problems, right? For instance, in speech recognition that go beyond that.
Let me think. Well, I mean, for a start, like, although clearly there's applications where you want to have one system, I still feel like there might be a space in the future for having a separate system just because of efficiency and computation and stuff. Like when people invented iron, we don't make buildings out of solid iron, right? Even though they'd be stronger and more elegant than the buildings we have. We have the absolute minimum amount of iron that's necessary to keep the building standing up. And I feel like at some point people are gonna start optimizing these things, and they're gonna keep revisiting the architecture of the systems, and it's not just gonna be one huge blob that accesses a trillion parameters on each step, right? It doesn't make sense from an engineering point of view.
Yeah, there might be also single architecture which are flexible, right? Single architectures like they
I suppose that's
activate.
right.
Yeah,
Something with like I really like the idea where the internals of the network is all conditional and it can decide which
right.
parts it wants to evaluate. But the problem is it's so incompatible with GPU computation, right? Conditional is just so slow.
Yeah,
I almost feel like we'd be going down a different path of neural networks if it wasn't that we were using GPUs. Like if everything was on a sequential CPU, we'd be investigating quite different things, I think. And who
yeah, that's
knows, maybe
actually
some of those
interesting.
things
Yeah.
would be really, really good.
Yeah, I also agree on your point of view, like like conditional computing, where you have like based on the input signal, you activate different
Yeah,
parts of the network. That's actually very
yeah,
interesting. Let's see how things evolve. Maybe there is a
yeah.
question
And I
for
think
you.
there still
Yeah,
might be a place for that kind of stuff. Like suppose you're
yeah,
building a tiny robot and it has just a little CPU. Uh, I assume you might want to do things like that on that.
yeah.
Uh, and even if it's probably going to be slower to train, but it might be worthwhile to train it in some slow way just so that it's super fast to execute.
Yeah, so yeah, interesting point of view. I think definitely there is like room for things like that. Let's
Yeah.
call it conditional computing
But
or like
one of the
or
reasons that I don't like to be doing all this LLM work with multimodal and everything is that I feel like imagine you're digging for diamonds and you know that a lot of people have walked through this particular patch of ground already looking for diamonds. Like it pretty much guarantees that there's going to be nothing easily accessible, right? Because people have been tramping through there. Whereas if you go to a patch of ground that nobody's really looking at, yeah, maybe it's a type of diamond that nobody wants right now, but you're more likely to find something interesting.
yeah, that brings me to the to one general question. Like there's Mohamed Adel who is like, I'm planning to pursue a PhD in the field of speech. What are some
Mhm.
promising or emerging research topics in the area over the next 4 years?
Hmm. Let me think.
We already
Uh,
discussed something, but maybe you have like other ideas.
let me think. Well, I think I know there's already a lot of people working on this, but I feel like model discretization and there's probably a lot of room for work in that kind of area, because I think a lot of times for deployment, the limiting factor becomes the storage of the model rather than the CPU time. And then you have to worry about the encoding of the model, like how many bits it is, what's the encoding, does it use code book entries, things like that. Of course, that's, you know, that's not going to be a super exciting research topic, but it might still be useful. What else? I mean, TTS is still interesting, like especially with things like dialogue generation. We're also interested in TTS partly because Xiaomi needs is building one of these kind of voice agent thing, and you need to have dialogue generation to simulate training data for that. It turns out it's not even that hard if you use these flow-based methods. They're remarkably effective. What else? I don't know. I find it hard to get excited about these things right now. The whole field feels so played out. I know there have been times in the past when it felt played out and it turned out not to be played out at all. Like there was a time like after things like minimum FMPE and things like that, that there's a time around that we were still using Gaussian based models that it felt like nothing was changing. And then of course neural networks came along and everything changed.
Okay, good. Sam, do you have like a question? Right, because we on the microphone.
One quick question. I was wondering if you have any interest in explainable speech processing, interpretable models, things like that.
I don't know. Like to me, there's something a bit fake about this whole explainable model research, because I feel like none of these explanations are actually really explanations. Like you can always come up with an explanation that kind of feels like it might make sense, but it's never a full and complete explanation.
Right.
And I feel like the only really valid reason for doing that is to pull the wool over the eyes of auditors, or like sometimes in the insurance business for like regulatory reasons, you need to be able to explain your models. But I feel like it's fundamentally somehow fake.
What about interpretable models to begin with? Like not explanations, but like interpretable.
Yeah, but then you're limiting yourself to really bad models like decision trees, and we know that there's like a very low limit on how well those kinds of things can perform.
The prototypical networks seem to be working well, like in medical imaging and things like that.
What kind of networks?
Like prototypical networks, like
Oh,
ProtoPNet, things like that.
well, yeah. I mean, I guess that there's going to be a trade-off, but I'm also a little bit skeptical about the real usefulness of these things. Like I feel like that the main reason you might want to do this is because someone somewhere in the command chain just prefers it to be so-called explainable. But in reality, I just don't know if I believe these explanations.
Mm.
Yeah, that's actually
Okay.
a great point of view. Interesting, stimulating, right? So we are also trying to work on interpretability, so we are really doing our best to. But I agree. I understand your point of view. Okay. Are there other questions like for Dan? So Pune, what do you think we should do?
Yep, I think that's great. Thanks, Dan, for the talk, and thank you,
Very
Mirko, for
late
the
here anyway.
discussion.
Thank you.
Thank you. Yeah. Our next session, we have Leda Sari. She's going to talk about the voice box model and its application. Looking forward to meeting you all next week.